Hey everyone, welcome. Today, we're going to pull back the curtain on some of the most ingenious yet kind of overlooked tools in Python's standard library. We're going to explore the hidden helpers that make the apps you love actually tick. I mean, really think about it for a second. You tap, you click, you scroll, and things just seem to work. But behind that smooth, seamless experience, there's a constant, furious battle going on against total chaos. And that's exactly what we're going to dig into today. We're going to meet these hidden helpers, the real unsung heroes of the code that powers our entire digital world. All right, first up, we've got a classic problem. Just imagine a hospital emergency room, a computer's processor, or even a video game trying to render graphics. They all face the exact same question. Out of a million things I could do, what's the most important thing to do right this second? The solution is this really clever, super efficient data structure called a priority queue. And in Python, its implementation is in the heap queue module. The name, heap queue, kind of gives the game away. It's a queue that uses a special structure called a heap to make sure the most critical item is always ready to go in a flash. Okay, so how on earth does it work? Well, it all comes down to one single, beautifully simple rule, the heap invariant. In a min heap, which is what Python uses by default, every parent item is smaller than its children. This one rule cleverly makes sure the smallest or highest priority item is always sitting right at the top, ready to be grabbed. Now, this comes in a couple of flavors. Python's heap queue is built for min heaps, which is awesome for, say, figuring out the next task on a to-do list. But with just a tiny little tweak, you can also create max heaps, which are great for finding the largest value in a big, continuous stream of data. And this is where the real genius of the heap comes in. It's efficiency. When you take that top item off, you don't resort the whole darn thing. No way. Instead, the very last item in the list just jumps to the top. Then it simply sinks down, swapping places with its smaller child until that main rule is restored. It's so clever and fast, meaning even if your list doubles in size, the work to fix it barely increases at all. All right, let's switch gears to our next big challenge. Computers are all about logic, right? They do exactly what you tell them to. So how in the world do you get them to do something completely unpredictable, like shuffling a playlist or deciding where an enemy should pop up in a game? Well, the answer is this kind of mathematical magic trick, a pseudo-random number generator. It's a really smart algorithm, like Python's Merz and Twister, that spits out a long, complex sequence of numbers. Now, the sequence is totally predictable if you know where it started, but it's so incredibly long and jumbled that for you and me, it looks totally random. And this brings us to probably the most important warning you'll hear today. Because it's pseudo-random, it's not truly unpredictable. That's why the official documentation gives this very stark warning. For anything, and I mean anything, that involves security or cryptography, you absolutely must use the secrets module instead. That module gets its randomness from truly unpredictable sources in your computer. But look, for everything else that isn't about security, the random module is your best friend for creating a little chance. Need a random number for a dice roll? Bam, Randint. Need to pick a random card from a deck? You got it, Joyce. Want to shuffle that whole deck? Shuffle. It's the engine that powers digital probability. Okay, so we've gone from creating chaos to, well, now we need to team it. A running application is constantly chattering away, generating status updates, warnings, errors, you name it. And without a system to manage all that, it just becomes a fire hose of noise. Python's answer to this is just brilliant. It's a module called logging, and its secret sauce is something called handlers. You can think of a handler like a smart postal service just for your app's data. It takes a message and knows exactly where it needs to go. And you won't believe how flexible this is. Want to see messages pop up in your terminal while you're coding? Yep, there's a stream handler for that. Need to save everything to a file for later? File handler. What if you need to email a critical error to a system admin? There's an SMTP handler for that too. It's an incredibly powerful system for directing information exactly where it needs to be. Now, one of my absolute favorite tools in this whole module is the rotating file handler. You know how log files can just grow and grow until they eat up your whole hard drive? Yeah, this thing solves that problem automatically. So imagine your log file, app.log, is getting full. Once it hits a size limit that you set, poof, it gets renamed to app.log.1 and a brand new empty app.log file is created. If app.log.1 already existed, it just gets bumped to app.log.2 and so on down the line. It's such a simple, elegant way to keep your logs tidy without you ever having to think about it. All right, for our last problem, we are tackling a huge one. Maybe the biggest one of all, trust. In a world where we download and run code from all over the internet, how do you know the code you just got is, the actual code the developer wrote and not something nasty that a hacker slipped in? The solution, which is now being rolled out across the Python world, is a kind of digital seal of authenticity. Its official name is an attestation. You can think of it as a cryptographically signed promise that says something like, I, the author, built this file and here is my unbreakable digital signature to prove it. So if you were to crack open this digital seal, you'd find two main parts. First, there's the proof of who signed it, their digital certificate. And second, you have the envelope itself, which holds the actual claim being made, the statement, along with that all-important cryptographic signature that proves it's the real deal. And this whole thing lets your computer play detective. When you download a package, your installer can automatically run through these 4 checks. It checks the version. It makes sure the certificate is from a trusted source. It confirms the file's contents perfectly match the statement. And finally, it verifies that cryptographic signature. If all 4 pass, you can be pretty darn sure the code is legit. Whew. Okay. After that whirlwind tour, let's just take a breath and look back at the incredible, invisible genius we've uncovered today. We saw how HeapQ brings order to absolute chaos with just one simple rule. We learned how pseudo-random generators create the illusion of chance, but with a huge security warning. We saw how logging handlers act like a smart postal service for data. And finally, how attestations are building a cryptographic chain of trust for the software we all rely on. And listen, these are just 4 examples. The software you use every single day is filled with thousands of these elegant, clever solutions, all working silently in the background. It really makes you wonder, doesn't it? What other invisible geniuses are out there just waiting to be discovered? Thanks so much for digging into this with me.